Many people think AI is a miracle, a digital brain that can think, imagine, and make decisions. That's an illusion. If we get to the root of it, there is no consciousness there. There is only linear algebra. In this video, we will thoroughly analyze it mathematically. Welcome to the AI Masterclass. AI is actually just a function because functions
describe the world. Everything is described by functions. The sound of my voice on your eardrum, function. The light that's kind of hitting your eyeballs right now, function. The entries you put in your random matrices, function. It's all function. Different classes in mathematics, different areas in mathematics study different kinds of function. High school math studies second degree one-variable polynomials. Calculus studies smooth one-variable functions. And it goes on and on. Functions describe the world.
Therefore, fundamentally speaking, AI is simply a mathematical function. It has one goal: to find the most accurate mapping from input X to output Y. The problem is that reality is messy. Human facial patterns and market movements are never linear. Try to imagine this curve depicting densely packed data points. This is where the universal approximation theorem comes into play. We use simple function pieces from each neuron to mimic this complexity. We force thousands of these small lines to adjust their shape until they closely resemble reality. The simple conclusion is that the more neurons there are, the more accurate the approach will be. Next, we move on to the structure of neurons. This is the basic anatomy of a neuron. Neurons always have inputs, weights, and biases. The way they work is that they receive inputs, multiply them by weights, and add them to biases. Mathematically, this is simply a linear transformation. Then, how does it work in real life? Let's take a simple example: the decision to buy a watch. When we want to buy a watch, there are at least 3 factors that we consider, usually being the price, the design, and the brand. We will try to interpret this with what we just learned earlier. We substitute numbers. For example, we give the price input a score of 5, but because the price is high, we force the weight to be -2. Then we give the design and brand input a positive weight, for example. And let's calculate. After performing the calculation, we get an output of 6. What does the number 6 mean? Nothing, before we give it a limit or activation function. In the past, AI used sigmoid. This function forces any result to fall within the range of 0 to 1. It is good for probabilities, but it limits AI too much to understand deeper intensities. That's why we switched to ReLU. Here, negative values are forced to 0, but positive values are allowed to shoot up without limit. It is this break at 0 that breaks linearity, giving AI the freedom to process abstract logic without being constrained by maximum limits. From the previous example, we know that a single neuron will never be enough to process the complexity of the real world. To achieve optimal results, we need a massive network that operates in parallel. Here is the anatomy. The input layer receives raw data. Hidden layers extracts abstract patterns, and the output layer makes the final decision. The problem is, calculating each of these connections one by one, from node to node, is computationally infeasible. It's too slow and inefficient. So let's perform a mathematical substitution. We'll eliminate the individual terms and reduce them to a linear algebraic equation. Z equals WA plus B. Look at this. We're explicitly cramming millions of weight parameters into a single 2D matrix. Thanks to this compression, the computer can perform millions of calculations in a single processor cycle. If we continue to force a linear model, the neurons will remain forever trapped along a straight line. Since we know the real world is complex and curved, a purely linear AI will never be able to learn any abstract patterns. Initially, we use the sigmoid function. This function mathematically transforms the raw output and forces it into the range of 0 to 1. If the value is greater than 0, the neuron is forced to activate. If it's less than 0, it's forced to deactivate. But let's look at its fatal flaw. At the ends of the curve, the line is perfectly flat. Because the gradient is 0, the calculus breaks down, and the AI will stop learning permanently. That's why we switched to ReLU. Here, negative values are forced students to 0, instantly deactivating the neuron. but if the value is positive, it's allowed to shoot up without limit. This single simple function forces a linear space to become curved. Without this break, the multi-billion parameter AI we know today would be nothing more than a standard regression calculator. When it's first turned on, the AI is blind. It processes incoming data, makes predictions through its neural network, and spits out the results. The guess was off. This is where the cost function comes into play. We take the difference between the guess and the actual value. Then we square it. Why square it? Because we want to turn all negative numbers into positive ones and penalize guesses that are off the mark. This is our error term. So how do we reduce this error? We need calculus. Using the chain rule, backpropagation, the AI traces its network from back to front. It has only one goal: to identify which neuron is most responsible for the error. Now that we know where the error lies, we'll use gradient descent. Imagine this is a section of the loss landscape. Since the gradient always points upward, we force its value to be negative. Look at this pink arrow. It calculates the gradient. The AI evaluates the situation, calculates the vector, then takes a step backward, colliding with gravity. It stops, calculates again, and takes another step. These steps are executed continuously until the error reaches absolute zero. The learning process in AI is no magic trick. It is purely a calculus-based evaluation that forces the ball to roll down the valley. Forget the rolling ball analogy. Today we're diving straight into the inner workings of the neural network. Since there are 3 neurons in the hidden layer and 2 in the output layer, this configuration requires a 3 times 2 weight matrix. These 6 connection lines are the variables we'll be calibrating. View the data stream in real time. The data is processed through weights, summed at the Z preactivation layer, and then mapped to the range 0 to 1 by the sigmoid function to produce the predicted value y hat. We compare the red prediction with the green actual value, and then calculate the total error using mean squared error. Now let's perform backpropagation. Let's take this specific weight, W11. How do we know how much this weight contributes to the total error? We use the chain rule. We trace the error path backward. Note the rationale. First, how far off our prediction is. Second, the derivative of the sigmoid function. This acts as a gatekeeper. It determines how sensitive the flattening curve is to letting error through. And third, the input entering this path is H1. This is the visual highlight. The problem arises when we want to update the weights before the hidden layer, specifically H1. Notice the lines. H1 is a double contributor. It contributes errors to both output 1 and output 2. Therefore, the total gradient for H1 must be the sum of all error flows that hit it. The more neurons in the output, the more error flows we must sum when backtracking the error. So the conclusion is,